All right, welcome to page 3 of the notes today. We're going to start with example 4. Determine by inspection at least two solutions of the given first-order differential equation. Don't really like doing inspection. This is the only time we're going to do inspection. The rest of the time, what we're going to be doing is we're going to be solving these through integration. And we'll have techniques to solve. But this one's just really like, okay, look at what we have and see if you can figure out what, these solutions would be. And so in this case, we're looking for, okay, where would, when we take the derivative of our function, if we multiply that by x, it's going to equal 2 times the original function. Well, the first, one is it's really easy. So we'll say, okay, well, if y is equal to 0. So here's one solution, y is equal to 0. Because when I take the derivative of that, it's just going to be y prime is equal to 0. And so when we plug it in, we're going to have x times 0 is equal to 2 times 0, and 0 equals 0. So it works out, it checks out. So there's the first one. Usually that's one that you're always going to check first, especially when you have, just the derivative on the left and y on the right. Then y equals 0 is always going to work. Now, for the next one, we need to come up with another one. Think of, okay, when can I take the derivative of y? And when I multiply it by x, I'm going to get the derivative times x is equal to 2 times the original function. And so the next one, hopefully you can tell, because that's, 2y, let's try to make it y is equal to x squared. All right, and again, you could try y equals x. I'm just doing these because I know which ones are going to work. And so if we do y equals x squared, then I take the derivative of that, y prime is equal to 2x. Let's go ahead and substitute it in. So we'll substitute this into x times y prime, which is going to be 2x, 2 times x squared for y. We're going to get 2x squared is equal to 2x squared. And so here we found both. So just by inspection means we're going to look at it and try to figure out what our solution would be. And so here we have our two solutions. All right. Could there be more? Yes. But, finding a solution by inspection, it's really just you looking at it and trying to determine, okay, what would the actual solution to this be? So, we're not really going to dive too much into that because this is the only time we're going to be looking at this. So this is not going to be very helpful for us in the future unless, you're just looking at something, I can just tell. The thing is, what we're going to be dealing with, you're not going to be able to look at and just tell. All right, now, the next one, it says, so solve. So here we have our differential equation. Notice that our differential equation is going to be equal to a function in terms of, x and y. It could be, especially with implicit differentiation. And so our differential equation could equal a function in terms of x and y, and it's going to be subject to an initial point. We're going to talk about the existence and uniqueness of a solution, existence of a unique solution. And so what we're going to do is we're going to let R be a rectangular region in the xy plane defined by, and then we're going from A to B and C to D. So we're just kind of, we're closing up our space in where we're going to be defined at. And it's going to be around a point that we have. And that contains a point x sub 0, y sub 0 in its interior. If x and y in the partial derivative of our function with respect to y are continuous on R, then there exists some interval I sub 0, x sub 0 minus h, x sub 0 plus h, where h is greater than 0, contained in a and b in a unique function y of x defined on our interval that is a solution of the initial value problem. So pretty much what we're going to be doing is we're going to be given a derivative. We're going to set the derivative as our function, and then we're going to take the partial of that. And if they're both continuous on R, then there exists, some interval where we're going to have a unique solution. And so pretty much what we're doing is we're just trying to find intervals. Again, this is something that's not going to show up a lot after today, especially in the future. But I do want to show you, everything that is in the text when it comes to just the introduction to differential equations. So in problems So here's your example 5. We're going to determine a region of the xy plane for which the given differential equation would have a unique solution, whose graph passes through a point x sub 0, y sub 0 in the region. So the first thing we want to do is define our function. So we're going to find f of x, y, and then we're going to determine, okay, what is the interval where it's continuous. And so if we have the function the square root of x, y, this is going to be continuous along where if x is greater than 0, then y has to be greater than 0. And if x is less than 0, y has to be less than 0. And hopefully you understand that because it's x times y. If they're ever different values, if one's positive, one's negative, we're going to have a negative underneath the radical, and we're not allowed to have that. So the two intervals that we would be continuous in would just be where they're both positive or where they're both negative. Now let's take the partial. So we're going to take the partial derivative of f with respect to y. And so we can look at this as, all of xy to the 1/2 power. And so then we'd bring a 1/2 out in front and then take the square root of xy. All right. And according to this, the same rules apply. For this, we could actually be equal to, but down here, we're not allowed to have those y values, equal to 0. So we're going to say for our unique solution, or where we would have a unique solution, it would be in any region where, and because this has to be continuous, we actually don't want those endpoints, because if we're at an endpoint, then we're not going to be continuous on the right side of that. So let's go ahead and get rid of these. And so where x is greater than 0 and y is greater than 0, or x is less than 0 and y is less than 0. And that's it. We just have to determine where they would be continuous at. And again, we can't use an endpoint, even though we could be 0 for, top for x, but, the bottom could be for y. Because it's at an endpoint, it's not going to be continuous, to one side of that, either the left side or the right side. All right, now, oh wait, that's it for this one.